Welcome. Thank you for being here. I was asked to talk a little bit today about chemical safety. So what I did was I looked at all the incidents we've had here on campus that involve chemicals, either someone being exposed to it. Incidents we've had, you probably heard of the incident we had up in Heritage. In the meeting we were in yesterday, we talked about someone in their dorm cleaning motorcycle parts. We'll mention a few things like that. And some incidents we've had here on campus. And so as I looked at all of those, I came up with my list of the top 5 things that seem to contribute to chemical incidents. And that's what we want to talk about. So the first one is physical form. That one we're going to be looking at, is it a solid, a liquid, a gas? What happens as it goes from a solid to a liquid or a solid to a gas, that kind of thing. Next one is vapor pressure. This is how much it evaporates, basically. Vapor density is when it does evaporate, do the vapors go up or down? We'll talk a little bit about that and why that relates to safety. pH, that's how acidic or basic something is, acid or alkaline. And then we'll wrap it up talking about some incompatible mixing. So, first thing, what do ice skating, frozen water pipes, and that blown up fume hood have in common? Any thoughts?
Pressure.
Pressure.
Temperature.
Pressure and temperature. And how that relates to the physical form of it. So, let's talk about this for just a minute. This is a phase diagram of water. Basically what it says is, and notice that it's not to scale. We have basically 0 here, 100 here, and 274 out there. And we have 0 here, and 1 here, and 218 right there. So this is not to scale. But what it does tell you, though, is at a given temperature and given pressure, it tells you whether water is a solid, ice, liquid, or water vapor. And so, for example, if you're down here right below the triple point at 0 degrees C, 32 Fahrenheit, and you're at 1 atmosphere of pressure, which is about what we're at here, a little bit below, water exists as ice. And if you increase the temperature, it crosses that line and becomes water. So for example, when you go ice skating, you have that thin metal blade sitting on the ice, and your body weight puts pressure on that blade. So if the ice is down here at 1 atmosphere and 0 degrees and it's at ice, the weight of your body on that blade pushes down. The increase in pressure makes it cross the line from ice into water, and you get a very thin layer of water in between the blade of your ice skate and the ice in the rink, which allows it to slide nice and easily. And then as soon as you go past it, the pressure drops because your weight of your body is no longer on it. Pressure drops at the same temperature. It crosses back over the line and it refreezes behind you, which is why the ice skating rink doesn't all melt when the hockey players are out there going nonstop. So, and then the same thing happens up here at 100 degrees C, 212 Fahrenheit, and 1 atmosphere. You go, water starts to boil and becomes a vapor. Now, the thing to know about that is, as water freezes and goes from a liquid to a solid, it expands. Water is kind of unique that way. Most other things do the reverse. They go from a solid to a they expand as they melt, whereas water does, which is very nice for fish, because otherwise if it wasn't, the ice would freeze on the top and it would sink to the bottom, and over the winter the lake would fill up solid ice and would kill all the fish. So God had a pretty good plan for making it less dense. So how does this relate to frozen water pipes? Water freezes, it expands, and it bursts your pipe. Well, here's an incident we had over in the Clyde building a couple of years ago. Now, this reaction vessel here is about 1/2 inch thick. It's 304 stainless steel, and that disc is, or that vessel is about 3 inches in diameter and about that tall. Now, think about this for just a minute. This, you see the curvature, the bow in that disc? That used to be perfectly flat. Now think, 1/2 inch thick, 304 stainless steel, a disc that big around, how much pressure does it take to bow half-inch thick steel that much? A lot. Who has the safety data sheet for aluminum chloride? Okay, so flip open to the tab there and read me off the density. I think it is maybe in blue, the one that's 2.4. Okay, what is the density of aluminum chloride at room temperature?
60 degrees Celsius. Okay, 2.44 grams centimeter.
2.44 grams per cubic centimeter. So picture like a little sugar cube, right? About a half-inch square. If that was made of aluminum chloride and you put it on the scale, it would weigh about 2.4 grams. Now, you melt aluminum chloride, it becomes a liquid. What is it at its melting point?
392 degrees Fahrenheit at 1.3 grams per cubic centimeter.
1.3. So when it's a liquid, it's 1.3. When it's a solid, it's 2.4. As you melt it, where does that other 1.1, 1.2 grams go to? It's got to go somewhere, so it expands. Well, what happened in this incident was they packed that stainless steel vessel full of aluminum chloride, didn't leave any vapor headspace on it, and then put it on a hot plate and melted it. And when it reached its melting point, the pressure inside there blew the thing apart and destroyed the fume hood. So just to give you an idea here, it blew the top out, blew the side off. These are all tempered glass. So what I did for this picture is these panes here slide, like a sliding glass door in your house. I slid those two open, and so this picture, I'm standing right here looking into the hood. So there's the one sash, there's the other one over there, and I'm looking in. That hole that you see there is bigger than a basketball. Now that countertop there is like 3/4 inch, fiberglass reinforced, phenolic resin, bulletproof, impervious to everything, and it blew a hole right through it. I mean, just a phenomenal explosion that just destroyed the fume hood. And the only thing they did was put some aluminum chloride and a few other things. It wasn't pure aluminum chloride, but they packed it in there, sealed it shut, and put it on a hot plate. Now, there was no malicious intent there. They obviously didn't do that intentionally, but it was a simple oversight of not knowing what happens to that material when it goes from a solid to a liquid, and not knowing the properties of the chemicals they're working with. So let's talk a little bit about vapor pressure and vapor density for a minute. So this is basically evaporation. So when you have a liquid, if it has a fairly high vapor pressure, the molecules of whatever it is, acetone, gasoline, benzene, whatever, some of those molecules will have enough energy that they just escape off into the air. Water will do it. Water evaporates. And we'll talk more about that here in a minute. But you notice all those gases escaping are all above the liquid level. When they happen below it, when you heat it up, there's enough energy in them that they create a gas down below the liquid level, and that's when you get boiling. That's the difference between boiling versus evaporation. So we'll talk more about vapor pressure here in a minute. Vapor density is after those vapors do come off and they're in the air, do they tend to go down to low-lying areas or do they go up? So for example, air as a reference value is about 1. Carbon monoxide is very slightly less than 1. So what that means is you have your plugged vent on your furnace in your house, or you decide to bring your barbecue grill inside the house and burn it inside instead of outside, and you have all this carbon monoxide building up. The vapors will not, like a helium balloon, they will not go out and up and into the atmosphere and disappear. They don't go down and hug the floor to where you're fine unless you're laying on the floor. They just mix in the air. And it just floats there and stays there, and you're continuously breathing it because it's right in your breathing zone. And when the concentration of it gets high enough, boom, it takes you out. Now, for hydrocarbons, so this is methane, ethane, propane, butane, gasoline, diesel, acetone, methyl ethyl ketone, benzene, all of them. All hydrocarbons other than natural gas, methane, all the others have vapor densities that are greater than 1, which means that in air, they will tend to find low-lying areas, and we'll see why that's important here in a minute. The rest of them will all pretty much dissipate and hopefully take care of themselves. So let's back up for just a minute and talk a little bit more about vapor pressure. They have a device. This is under vacuum, so there's basically no air in here. And in the little trap here, they put in some mercury. So there's no air in here, and they sit at level. So what the idea is, you take your liquid, you put it in here, and as it starts to evaporate, those molecules exert some pressure, and it starts to put a pressure downward on this column of mercury here, and it starts to push it down on one side and up on the other. So the vapor pressure is a measure of how far is it from there to there. And it can be given in millimeters of mercury, inches of mercury, hectopascals. I mean, they're all, you'll see them on safety data sheets, different units, but it's like feet versus yards. It's just a different, you can convert back and forth. We'll see that here in a minute. So, for gasoline, now just to compare, the vapor pressure of water is about 17 millimeters of mercury, so about 3/4 of an inch at room temperature. 20 degrees C is about 70 degrees Fahrenheit. So let's back up here a minute. So if you were to put water in this device, what it's saying is you'd get about 3/4 of an inch of mercury pushed up in that tube. So, looking at diesel, the vapor pressure of diesel is less than 1 relative to water, which is at 17, but you notice the vapor density is 3, quite a bit heavier than air. So diesel vapors, although there aren't a lot of them, especially at 20 degrees C, what is there will tend to go low. Gasoline, by contrast, still has about the same vapor density as diesel, but the vapor pressure is about 450 to 750 millimeters of mercury, substantially more than water.
So it evaporates or off-gases more.
Exactly. So gasoline is much more volatile, has a higher vapor pressure, it evaporates faster, there's more of it coming off into the air. So let's see a quick example of that. I went over to the gas station and for about $20 bought these 2 vials of gas, because gas is getting very expensive. So what I'm going to do, this is just regular number 2, whatever they call it, diesel fuel, same as you'd put in your car or your truck. So we'll put a couple of drops of diesel fuel down in there. And we'll cap that one off. And then we will come over here and we'll put a little gasoline. This is just I bought the cheap stuff, the 85 octane. But we'll put just a few drops of gasoline in this one. And then we will cap that off and move that very far away. Now, watch what happens when I put the lighter in by the gasoline. Now you notice I don't even have to touch the flame. I got down within an inch and a half or so of the gasoline, and there were enough vapors there because of the vapor pressure. There was enough gas vapor in there that it ignited it, and then it went down and lit the liquid that's down here in the dish. Now compare that with diesel fuel, and you can put the flame right down there on top of it, in direct contact with it, and it doesn't light. That's the difference between flammable and combustible. Now, this one, as you get above 20 degrees C, as you start heating it up, yes, it will get higher and higher vapor pressure, because they're kind of related. As temperature goes up, vapor pressure goes up. But for right now at room temperature, there's just not enough vapor coming off of there to allow the diesel to burn. So the take-home message is, as you look at a safety data sheet and as you're working with chemicals and trying to be safe with them, generally the higher the vapor pressure, the more dangerous it is. So let's talk about another example of that, of vapor density. So carbon dioxide, dry ice, has a vapor density of 1.5. So again, air is 1, so carbon dioxide vapors are also heavier than air. Not as much as these, but the thing is, though, is for carbon dioxide, this is the phase diagram for it, like the one we looked at for water, except for this one, we stay down in this range. It never crosses into the liquid area because of the temperature and pressure. We go straight from a solid into a gas. We're crossing this portion of the line here. That's why it's called dry ice, because it never melts. It goes straight from solid to gas. Now, because the vapor density is greater than 1, I put some dry ice down in the bottom of my pitcher here, and it's been crossing that line here, going across there, and as it goes from a solid into a gas, because it's heavier than air, it stays in there, and as it rises, it pushes all the air out of the pitcher. So hopefully, if we've done this right, what we've got is a pitcher full of carbon dioxide gas in there. And again, the vapor density is heavier than 1, so it tends to go to low-lying area. So let's light our candle in here. And then watch the candle and watch what happens as we pour carbon dioxide down our tube here. So you notice put out the candle. So what happened is the heavier than air gas in here travels down the tube, and carbon dioxide is a fire extinguisher, so it puts out the candle. Now, the same thing will happen with gasoline vapors. Had I put gasoline in here instead of carbon dioxide and done the same thing, and it finds an ignition source, it would have ignited the vapors, and there would have been a flash of fire up through this tube into here, and we'd have got a fireball flashing out of my pitcher up here. So the safety message is, if you're at home or at work, doesn't matter, and you've got a flammable liquid, those vapors will tend to go to low-lying areas and will travel out and find an ignition source. So if you're out working in your garage and your water heater with the pilot light, or your brother-in-law using your electric drill or whatever, if there's an ignition source over there, those vapors, because you've got your open can of gas cleaning your parts or pouring in your lawnmower or whatever, those vapors can find that ignition source and just like this, flash back to where you are, if there's enough vapors there, and ignite you. So you really want to have good ventilation and make sure that you don't build up enough of a flammable atmosphere that you can have that kind of thing happen. And it's not just flammable. Here's another one. Notice we have up here at least 14 worker deaths since 2000 related to bathtub refinishing with stripping agents containing methylene chloride. Methylene chloride is not flammable, but this was enough of a problem that OSHA back in 2013 put out this warning. Have you ever seen the TV commercials for like One Day Kitchen and Bath? They come in, well, what they do, usually, not always, but usually, they don't rip out your existing bathtub and put in a whole new tub. What they do is they prep your old tub for a liner, and they put a new liner into your existing tub to refinish it. Well, to get that old tub ready to accept the liner, they put in this solvent containing methylene chloride. The problem is, methylene chloride has a vapor density of like 2.9, it's almost about like the other hydrocarbons, so it's much heavier than air, and it has a very high vapor pressure on par with gasoline. So it's putting off a lot of vapors, it's heavier than air. Well, so they reach down in the tub and they're like putting their goo on the tub to get it ready. Well, the vapors can't go down the trap in the drain of the tub because there's water in there, so the vapors can't go down the drain. They build up in the tub just like they did in that picture, and then the plumber, whoever comes in, sticks their head in there, and they get no oxygen, they pass out and drop into the tub, and by the time the homeowner, who's off in their kitchen doing whatever, comes in to check on the progress, the guy's lying there dead in the bathtub. And it's killed at least 14 people that we know of doing that. So it's not only flammability, but anytime you have those heavier than air vapors, you need to make sure you have adequate ventilation and don't get into an area where you're in an oxygen deficient atmosphere. Okay, let's talk about the pH scale for a minute. Goes from 0 to 14. Pure water is right in here in the middle at 7. If you go way down here on this end, you have the strong mineral acids. So this would be things like hydrochloric, which is very commonly used in pools and toilet bowl cleaners and things like that. Sulfuric, which is in your car battery. You're coming up a little bit more. Lemon juice is about a 2. All the Coke drinkers here. If you ever looked at the label, Coke has phosphoric acid in it. At least the last bottle I looked at did. I'm assuming it's still in their formulation, but it's about 2.5 or so. So what you do is when you drink your Coke, then afterward you go drink your milk of magnesia, which has pH of about 10, and then that one kind of counteracts that one and they react and it becomes more neutral, which is why that's an antacid, because one offsets the other. Keep going up. Ammonia is about 11, bleach is about a 12, and then up on the way high end you get lye, sodium hydroxide, drain cleaner, those kind of things, about a 14. So, under the EPA rule, because they have to draw the line somewhere, they say that if you have an aqueous liquid, if the pH is below 2 or above 12.5, it's considered corrosive. Now, does that mean that at 2.1 it's not corrosive? No. It's a gradient scale. The closer you get to either extreme, the more dangerous it becomes because the more corrosive it tends to be. So, for example, you get hydrochloric acid, pH 0, sodium hydroxide, pH 14, that sodium hooks onto that chlorine and you make sodium chloride or just regular table salt. That OH hooks onto that H and you make water. So this 0 and 14 react and you get something reasonably close to about a 7. They neutralize each other. So when you have a chemical spill, what you want to do is trying to control the pH of either one of these by themselves is nigh unto impossible. It just takes a huge amount of water to do that, to dilute it to a 7. But if you can, say you have an acid spill and you have a bag of, say, sodium bicarbonate, baking soda, you spray that down, they will neutralize each other. It controls the pH and makes it much safer to clean up the mess. So that's kind of the way you would do that. Here's an example we had over in the Eyring Science Center a few years ago. Individual was working, had a bottle of concentrated sulfuric acid, pH 0. The bottle broke and it landed on their shoes. Now these are lightweight running shoes. So what you see here is that fine plastic mesh. So the shoes like ventilate and your feet don't get all sweaty when you're out running the marathon. And then underneath that there's like a little 1/8 inch thick layer of foam, and then you got, the sock and the inside of the shoe and all that. Now, how long do you think it took for the sulfuric acid to go right through that mesh and start chewing the top of his toes? It didn't even slow down. I mean, as soon as that thing dropped, he reported that he felt it gnawing on the top of his feet. So you can't even kick your shoes and get your socks off fast enough before you start having damage. So the idea is plug for PPE here. If you're working with these highly corrosive materials, at a minimum have some good solid leather shoes, preferably have some rubber boots that are impervious to the liquid, but make sure you keep that stuff off you. Here's another example we had. This one was over in the Nichols building. Individual was taking bottles of acid, in this case nitric acid, off the cart and putting them into this storage shelf here. One of them dropped and landed here on the floor and broke. Now these little runners that you see here, those are not splash marks. Those are where the splash started dissolving and buckling the epoxy paint right off the concrete floor. all this discoloration you see here, that part of the floor used to be all this color. It was, I mean, as soon as it hit, it just started blistering the paint, peeling it off, deteriorating it, discoloration, all that kind of thing, and it started almost immediately. Now, unfortunately, the individual that was involved in this was wearing safety glasses, but one of the drops went that direction and got in her eye. Now, we were able to get her to an eye wash very quickly. There was one nearby. We got her in, flushed the eyes for 15 minutes. She wasn't blinded, but there was some permanent vision damage there. And all it took was that one little splash drop for a matter of a second or two before she got to the eye wash, and the damage was done. So it becomes very important dealing with these kind of materials to make sure you have appropriate PPE on, keep it off you. Okay, let's watch this video real quick, and then we will talk about what happened.
A friend tells us Ryan Baldero was an amazing guy who was always willing to help others. The 32-year-old succumbed to fumes during a hazmat incident at the Burlington restaurant where he was the general manager.
We believe it's a tragic accident.
Burlington's fire chief says their investigation found the incident was caused by an inadvertent mixing of two common cleaning agents.
The off gases that are produced by the chemical reaction, it can be deadly, and unfortunately last night that was the case.
A worker used a solution called Super 8 to scrub the kitchen floor, but a second cleaner called Scale Clean had apparently been knocked over.
He stated that he saw the chemical actually turn to a greenish color and that he saw bubbles forming.
The worker escaped outside, but General Manager Baldera tried to squeegee the remaining solution away, the action itself causing more of a chemical reaction. Today, commercial cleaning crews were inside the closed restaurant as the fire chief determined the incident was an accident.
I want to make this perfectly clear that this wasn't an employee mixing two chemicals into a bucket. This was an employee using one chemical that unfortunately was not aware that the second product had spilled.
OSHA is also involved. They are investigating, and it'll be up to the Burlington Board of Health to decide when, if the restaurant will reopen.
Now, kind of a sad story, but let's talk about this for just a minute. Ryan, 32 years old, if you know the backstory on him, was reasonably newlywed. He and his wife had just had their first child a couple months before. I think the child was maybe 3 or 4 months old, something like that. I don't remember for sure. But this guy, I mean, he's working as a restaurant manager. He's not making $1 million. He's probably just out there trying to do his job, trying to do the right thing, trying to support his family. He's responsible for the restaurant. He sees a mess. His worker has to bail out because he's coughing and gagging and wheezing. And he's just trying to protect what he's responsible for. Goes in, starts squeegeeing it out. Well, what happened there? Who's got the safety data sheet for Scale Clean? Okay, so look on the front there. What is the appearance of Scale Clean?
What do you mean by appearance?
Down toward the bottom there should be highlighted.
Aluminum chloride hexaderate.
Okay.
Citric acid monohydrate.
Okay, so citric acid, so an aluminum chloride is a type of acid. We have citric acid there, so we have an acid compound. And next line down there, what's the appearance of it?
Appearance and odor is white or off-white granules, like coarse salt or sugar.
Okay. And does it have an odor?
No odor.
No odor. So you have a solid material here. It's a solid, doesn't have much vapor pressure, so you're not smelling it. And it looks like regular, like little granules of table salt or granular sugar. Now, we're not talking a big pile of it there on the floor. What had happened, as I understand it, was that it had spilled, they had cleaned it up, but there were still these little grains of salt kind of looking things that were in the cracks in the concrete and in the pores of the cement or wherever. I mean, trace amounts that weren't swept up all the way. Now, who's got the safety data sheet for Super 8? What's the primary ingredient of Super 8?
Sodium hypochlorite.
Sodium hypochlorite, also known as bleach. So what you've had here is bleach being mixed with an acid. Now, as you watch the news report there, you heard the fire chief say that the person involved saw that it bubbled and started to turn green. Well, when you mix bleach with acids, the reaction gives off, among other things, chlorine. Chlorine is a gas that you can see, unlike carbon dioxide. That one is green. So what he saw there was that reaction going on and bubbles of chlorine being given off. The problem with chlorine is when you inhale it, it reacts with the moisture, the liquid, the water in your mouth and your lungs, and as you breathe it in, it converts that chlorine and hypochlorous acid and other things into hydrochloric acid, pH 0, and it literally starts dissolving your lungs. And you start coughing up chunks of your lungs. And then, because your body's trying to get rid of this stuff, it starts pouring fluid into your lungs, trying to dilute it and get it out, and you get pulmonary edema and you die in your own fluids. And all the guy was doing was with the squeegee, trying to get this stuff out the door. Now, it probably didn't kill him immediately. My guess is he was probably coughing and gagging and choking. And it was, again, I don't know. It depends on the concentration and how much. But my guess is it was probably a while later before he finally succumbed to his injuries. Miserable way to go. But if you ever look at the bottle of Clorox, on the label it will say, warning, do not mix with other acids or other household cleaners. That's why. Well, you can also react it with ammonia, and it'll give off chloramine. Not as bad as chlorine, really, but that one is an irritant, and that one will take you out as well. So the idea here is not only does it become a pH kind of thing, but now we're moving into the incompatible mixing and things you don't want to mix together because you don't know what they do. So here's an example of this one. I went over to Lowe's, and for about $6 I bought this bag of Pool Shock. This one is calcium hypochlorite, and it's a white powder. That's the stuff you would put in your hot tub or your swimming pool to chlorinate it, kill all the germs. So it's readily available. You can go anywhere you like and buy that. After I left Lowe's, I went over to AutoZone or Pet Boys, I don't remember where, somewhere, and got my jar of .3 regular brake fluid. Now, those are two that very easily could be in half the homes in America, especially if you have a hot tub or swimming pool. Now, it's hard, you can't see here because the calcium hypochlorite, the Pool Shock, is white, and because of the contrast you can't see it. This crucible here is about that big around and about 1 inch deep. And I put about, maybe 1 tablespoon of Pool Shock down in here, and then with a pipette, kind of like the ones I used here for the gasoline, I put in about 5 or 10 drops of brake fluid. And notice that after I put the brake fluid in on top of the Pool Shock, I backed off and didn't touch it. So let's watch this video here and see what happens. So, imagine in your garage, you've got these two or similar things like those, an oxidizer and a fuel source. And because we're in an earthquake zone, you have an earthquake and those two fall off the shelf. Or one of your grandkids is out playing outside and the ball goes bouncing into the garage and knocks them off the shelf on the floor, and 60 seconds later, without doing anything, your house is on fire. Or you are here on campus somewhere and you've got these two chemicals sitting in a storage cabinet in your work area, and this is just plastic, it's high density polyethylene. It springs a little leak and some of it leaks over here and you get a reaction going. There's lots of plausible scenarios where these incompatible materials could mix and start a fire without even touching it. So it becomes very important when you've got things like acids and bases, oxidizers and organics, different classes of materials that are not compatible, make sure they're stored separately. So let's talk about a favorite incident that happened here on campus just a couple of weeks ago. Individual went and just got regular, this is a do-it-yourself if you want to, by the way. I'm not giving you instructions, I'm not condoning this, I'm just saying it's available to you if you so choose. But you didn't hear it from me, so you can't sue me. I'm putting out my disclaimer. But you go get regular sugar, any grocery store, Sam, just sugar. Then you go to like the garden center at Walmart or IFA Country Store, wherever you like to shop for garden stuff, and you can get a 20-pound bag of potassium nitrate. If you don't want that much, then you get the smaller jar of stump remover. Either one, they're both potassium nitrate. Potassium nitrate is analogous to the pool shock here. It's an oxidizer. And here you have your fuel. So this, same like we saw here, this is your brake fluid, this is your pool shock. Now, what the individual was doing in their dorm was they were mixing these two, making homemade rocket fuel. Now, fair credit here, just to be balanced, you can do this. It's not a tremendously high hazard. I've done it myself. The reason it's commonly called rocket candy. The reason it's called that, it's candy because it's half sugar, but you can mix this material, and if you've ever made like a model rocket, you go to the hobby shop, you buy the little kit, you assemble it, and then they usually have those little Estes brand rocket motors. They're like a cardboard tube about as big around as long as your finger, and they already have the propellant packed in there, and you put in your igniter and you shoot off your model rocket. You can make those yourself with this kind of material. And you just pack it in the cardboard tube yourself and light off and make your own rocket motor. So that's what the individual was doing, or something similar thereto, and here's what happened. The problem is they had a huge bag of that and a huge bag of that, and it was on the stove in a stock pot, and the heat ignited the mixture. Now this one takes off on its own. This one here generally requires a heat source, which happened to be right there on top of the stove. And because the material provides its own oxygen and things like that, those are very energetic fires. They're not like this one where you get this nice little gentle little flame going. No, this one, it takes off with a forceful flame, and they are very difficult to put out once they get started. And so it just basically erupted into the whole kitchen and basically destroyed the dorm. And again, just mixing things that are not compatible. So watch what you're working with. So what did we learn today as we wrap things up? The state of matter matters, whether it's a solid, a liquid, a gas. What properties does it have? Is it like water, that it expands when it freezes? Is it like aluminum chloride, that it expands when it melts? What does it do? Is it more hazardous when it's a gas versus a liquid? Know those kind of things. Generally speaking, the higher the vapor pressure, the more dangerous it is. The more stuff there is coming up into the air, whether it's flammable or toxic or whatever, the more of it isn't contained in that dish or in that container, the more that it's out in the air, the more hazardous it is. Vapor density, if it's less than 1, it rises. It's like a helium balloon. You let it go, it goes out, it goes, finds the holes in the roof and disappears. If it's greater than 1, it finds the low-lying areas and can find ignition sources or build up and create an oxygen-deficient atmosphere. And if it's about 1, it will just hang out fat, dumb, and happy in the air and just stay there. pH, avoid the extremes. If it's less than 2 or above 12, be aware that it's going to be corrosive, and we've had incidents on campus because of that. And last but not least, be cautious when you mix things together. Some chemicals just don't play well together. So, with that, what are you going to do now? Based on what you know, what we've talked about, what are you going to do differently?
Read the SDS.
Read the safety data sheet. Now, is every piece of information on the data sheet going to be relevant or important? No. Is there some very good, very useful stuff there? Absolutely. Should you read it so you know the properties of it? Absolutely. Good thing to do. Excellent. What else?
I think if I don't understand what a chemical can do, I probably should reach out to somebody who can help me.
Yeah, if you don't know, if you're new to the chemical, that's why OSHA has the Hazard Communication Standard and GHS and all these other things that are out there, so that employees, if you're working with chemicals, you're required to be trained before you start using with them. And if you don't know, go ask your supervisor, ask the boss, ask somebody who knows about it, ask the manufacturer, call them up and ask them, get some information about it. Absolutely. What else?
Be cautious how you store chemicals.
Yeah. If they're flammable, keep them in one of those, they're usually yellow, not always, but something that will contain the flames. Fire resistant, yeah, absolutely. If they're incompatible, give them secondary containment and keep the 2 tubs apart where they can't mix. Maybe wear some PPE if you're dealing with things. If you got flammables, wear a fire retardant lab coat or something like that. Corrosives, wear your goggles, whatever. All right, so we're done. Any questions or any comments about any of that? Okay, well, thank you for your attention. Thank you for being here, and we are done.